Welcome to The Explainer. Today, we're going to demystify the hidden systems and, honestly, the invisible math that secretly runs our modern world. I mean, have you ever stopped and wondered exactly how global supply chains route millions of packages perfectly on time? Or, say, how a hospital allocates its beds during a sudden crisis? Well, the answer isn't magic, and it definitely isn't just guesswork. It's actually a fascinating, highly structured science that was born out of sheer necessity during the absolute darkest days of the 20th century. So buckle up because we are diving right into the incredible detective story of operations research.
Let's jump right in by looking at a literal life-or-death puzzle. Okay, picture this. It's World War II, and you're a scientist working for Bomber Command. Your planes are returning from bombing raids over Germany, and man, they are just getting absolutely shredded by anti-aircraft fire. So you're tasked with analyzing maps of where these returning planes took the most bullet holes. The goal? Figure out where to add heavy armor to protect future flights. But here's the catch. Armor is incredibly heavy. You literally can't cover the whole plane, or it just won't fly. So you look at the data. The fuselage, the outer wings, the tail. They're completely covered in damage. So based on this damage map, where do you put the armor? Take a second to think about it. I mean, human intuition basically screams at you to armor the places with the most bullet holes, right?
Well, here's the shocking, totally counterintuitive answer that an extraordinary team of scientists, led by a guy named Patrick Blackett, came up with. They looked at those exact same maps and concluded you actually have to put the armor on the spots with absolutely no damage. Crazy, right? But why? Well, because the military was only surveying the planes that actually made it back. By process of elimination, if a plane got hit in the engines or the cockpit, the completely undamaged areas on those maps, it suffered a catastrophic failure. Those planes never returned to be counted in the first place.
And this historical puzzle right here gave us the textbook definition of survivorship bias. It's basically the fatal reasoning error of analyzing only the surviving cases while completely ignoring the ones that failed. If the military had just gone with their gut feeling on this, they would have armored the strongest parts of the plane and completely ignored the most vulnerable ones. That would have led to systematically wrong and frankly fatal conclusions. This whole story brilliantly illustrates exactly why human gut feeling simply isn't enough when the stakes are that high. We desperately need a systematic, data-driven approach to tackle complex problems.
Now, what's really fascinating about this is that Blackett's team wasn't just taking wild guesses. They were actually early practitioners of a brand new science. The Operational Research Society of Great Britain defines their field as applying the methods of science to complex problems to predict and compare the outcomes of alternative decisions. Okay, yeah, that is definitely a mouthful, but it really just boils down to two vital anchor concepts: scarce resources and optimal decisions. You see, operations research doesn't just look for an answer that kind of works. It uses these interdisciplinary teams of mathematicians, physicists, and engineers to systematically hunt down the absolute best, the optimal way to allocate limited time, money, and materials.
To really grasp where this science shines, we kind of have to contrast the types of decisions we make every single day. On one hand, we've got program decisions. These are repetitive, they're well-structured, and they happen under known conditions. Think of like a factory reordering inventory or a manager scheduling employee shifts. This right here is the sweet spot for operations research. A mathematical model can perfectly represent these variables and find that optimal path. But on the other hand, we have unprogrammed decisions. These are novel, one-off situations that happen under deep uncertainty. We're talking about deciding where to build a massive new corporate headquarters or launching a totally unproven product line. For unprogrammed decisions, your human experience, your intuition, and your gut instinct still carry the most weight. I mean, you wouldn't use the math equation to decide who to marry, right? But you absolutely should use one to route 1,000 delivery trucks.
The rapid history of this field is honestly just as fascinating as the problems it solves. Operations research didn't start in some quiet ivory tower. It was literally born out of extreme military necessity. Back in 1937, at the Bawdsey Research Station in the UK, A.P. Rowe started analyzing early warning radar systems. He realized that you had to study the whole operation, including the humans running the machines, to actually make it work. Fast forward to 1941, and Blackett's team, affectionately nicknamed Blackett's Circus, was optimizing World War II tactics. They saved countless lives just by figuring out the best convoy sizes and depth chart settings. And then in 1947, a massive breakthrough happened. George Dantzig invented the simplex method. This mathematical powerhouse basically allowed these military techniques to jump straight into civilian industry, turning operations research from a closely guarded wartime secret into a global industrial engine.
So how do these scientists actually solve these massive, unwieldy problems? Well, they use models. Think about it like this. If you want to explain an elephant to a small child, a super long verbal description about a gray mammal with a prehensile appendage, yeah, that isn't very helpful.
But a simple line drawing of a trunk and some big ears, that works perfectly. Now, obviously, the drawing isn't the real elephant, but it's a necessary simplification that captures the most important features. In operations research, mathematical models serve the exact same purpose for managers. They let us experiment with a massive, messy decision problem cheaply, quickly, and above all, safely. You can test things out entirely on paper or a computer, way before you commit millions of dollars in the real world, where mistakes are, irreversible.
But because the real world is just so chaotic and messy, how do we actually go about modeling it? Well, analysts categorize problems in 5 distinct ways to sort of tame that chaos. First, what's the structure? Is it physical, like a little toy car, or is it symbolic, using complex math? Next, what's the purpose? Are we just trying to describe what a system is doing right now, or is it prescriptive, where the math is actually telling you the optimal action to take? You've also got to think about the environment. Is it deterministic, meaning we know all the facts with absolute certainty, or is it probabilistic, where risk, chance, and randomness are throwing a wrench into things? By breaking down a wild, real-world scenario into these specific classifications, analysts can translate almost anything into workable math.
Now, all of these different models ultimately feed into one core methodology. No matter what kind of model you're using, the process follows 5 exact phases. Step 1, you formulate the problem. This means clearly stating your goal and your constraints. Step 2, you construct the actual mathematical model, identifying your decision variables. Step 3, you solve the model to find that optimal solution. Step 4, and honestly, this is absolutely crucial, you validate the model against reality to make sure it actually makes sense outside of a spreadsheet. And finally, Step 5, you implement the solution. Notice something interesting here? The heavy math only really happens in Steps 2 and 3. The real genius of operations research is correctly framing the problem in Step 1 and verifying it in Step 4.
Let's actually put this into practice so you can see just how powerful it really is. Imagine you run a company. Let's call it Green Build Construction. You want to manufacture standard and reinforced concrete blocks to maximize your profit. Seems simple enough, right? But then you look at your constraints. You only have a highly limited number of machine hours available every single week for mixing, molding, and curing those blocks. If you just guess how many of each block to make, you are inevitably going to leave money on the table, or worse, completely bottleneck your factory. It's a massive headache for a human brain to calculate on the fly. But by defining the decision variables, like exactly how many standard versus reinforced blocks to make, and turning those machine hours into rigid mathematical constraints, an operations research model will guarantee you the absolute optimal production number. It takes a wild guessing game and turns it into a guaranteed optimum, squeezing out every last drop of profit.
And this brilliantly illustrates the sheer massive scale of modern operations research. I mean, it has moved so far beyond its military origins of routing convoys and armoring bombers. Today, it silently optimizes our entire civilian world. It's literally the science behind hospitals allocating beds to minimize emergency wait times. It designs the layout of telecommunication networks so your calls don't just drop out of nowhere. It routes global supply chain freight so your packages miraculously arrive overnight. It plans the critical path for constructing massive skyscrapers. And it dynamically adjusts prices for airline tickets and ride shares in real time. Basically, if a system involves scarce resources and a specific objective, you can bet operations research is running the show behind the scenes.
As we wrap up this explainer, I really want to leave you with a critical warning, drawn straight from our historical examples. Remember that elephant drawing? A model is an incredible tool constructed to help us understand a problem, but a model is never the real system. It ignores things. It simplifies things. The math will always give you an exact answer based on the data you feed it. But if your data is suffering from something like survivorship bias, your perfect math will perfectly lead you to a disastrous decision. A model is meant to inform a decision, never to completely replace human judgment. So looking at your own life and work, are you going to automatically trust the math, or will you validate it against reality? How will you optimize your own scarce resources? Think about that for a bit, and always, always keep questioning the data.